Hi, welcome to the second live session of concept topology. Okay. Uh, so first, let me introduce myself. This is Shauri. Right now, I'm doing my. Hi, can you hear me? Can you hear me? Can you hear me?
Yeah, hi. I'm not a student. I'm from NPTEL team.
Okay, okay. Yeah, I.
Thank you. Continue.
Yeah. Hello, madam. I want to know since nobody has joined, should I start now?
Yeah, you can continue. You can start recording and you can do the session. That is not a problem. We'll be uploading it on the portal.
Okay, 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 madam, okay. So I had gone through such lecture. So sir has started from the compactness and the separation actually. So in the last week, the first session, we have discussed about the compactness of metric spaces. Today we shall discuss some problems regarding compactness in the topological space. Okay. So yeah. So let's start with some problems. Okay. So one second. Yeah. Yeah. Now can you please tell? Is my voice clear?
Yes, sir.
So So, you so do you know basics about the compactness in the metric spaces?
Yes, sir.
Okay, so would you please tell the definition of compactness in? Would you please definition? Yeah, metric compactness.
Okay, sir. Sir, a space is said to be compact if
Yeah,
for every open cover which cover that space, it has a finite subcover.
yeah, good. Okay, so right, yeah. So now this session is actually for problem solving and clearing doubts in the concepts and in sums also. So should I start directly with some problems or should I first go with some basic things like or some basic concepts and then should I start the problems? Please let me know. Please tell me, should I start with problems or should I start some basic concepts? Then do we start problems? Okay, problems. Okay, Fida. So it's a problems. Okay, so before starting the problems, let me ask some basic things. So do you know tube lemma? So do you know tube lemma? You can uh, say it in the chat also. Okay, okay. So Okay, first we start with some easy problems, then gradually we will move on to difficult problems. Okay. So, okay. So first question is that close. Sorry, is open 01 compact? Yeah. Can anybody please try that open 01 is compact or not? Anybody please that open 01 is compact or not?
So it is not compact. We
Okay.
can prove it.
Okay. Why?
So we can prove it by contradiction by assuming, suppose it is a compact, and we can take a open cover.
Okay.
So
So which open cover? I mean, you can take open cover. That's okay, but which open cover you will take? Please tell which open cover you take in order to show that it's not compact. What about others? Can anybody please tell why Open01 is not compact? Okay, so you have written in chat open cover. Yes, correct. Your answer is correct. Yeah, very good. So for those who don't know, or so let me discuss. So if we take the open cover UN with open 0 comma 1 by n, then open cover. Sorry, this is an open cover of open 01, but this does not have finite, so yeah, right, very good. So yeah, okay. Now,
So take n equal to 1, it's a finite subcover.
sorry,
The first element,
yes,
the first element itself cover all of.
yeah, okay, yes, you are right.
So if we take like the distance uh, like 1 by 2 to 1, slightly less than 1 by 2 to 1, like 1 by 3 to 1, and then 1 by 4 to 1 by 2.
Sorry, yeah, please repeat.
It's like if we take like 1 by 3 to 1 and 1 by 4 to 1 by 2 and 1 by 5 to 1 by 3, yes, 1 by 4 to 1 by 2, and like that if you continue,
Yes, yes.
then each is open, but
This also has
means
one.
1 by n plus 1, 1 by n plus 2 to 1 by n, maybe you can write.
Uh, yes, you are. This is also fine. Yes, this will work also. And here, we are in the first one. Here, this u will be actually this one. 1 by n comma 1. This will not a finite sum. Sorry. So, also second problem. So let tau and tau prime. The and let uh, so the question is follows: a tau and tau prime are two topologies on a space on a set X, and it is given that with respect to that topology, the space is compact and Hausdorff. Okay, then we need to check that either those topologies are equal or they are not comparable. Okay, so this is what you need to check. Two topology on a space is given, and it is also given that they are compact and Hausdorff. P2 means Hausdorff. Then you need to check either those two topologies are equal or they are not compatible. So the hint is that, the hint here is that if so hint is that here, if suppose we have a continuous function f from x to y, which is continuous plus bijective, and if x is compact, y Hausdorff, this implies f is a homeomorphism. Okay, this is the hint you can use in order to solve this problem. Also, this is the hint, and in order to start the problem, you can assume that suppose this is comparable, and then you show that this is exactly equal. Okay, let's try. Take your time.
Sir, by sir, these two topologies are equal. So, do we need to show that both the topologies are homeomorphic? Sorry, topological space are homeomorphic.
Yes, right. You are absolutely correct. But not only homeomorphic, you need to check that they are exactly same. They are exactly equal.
Oh, okay, sir.
Yeah. So basically, you need to construct a function which will give both homomorphism and the equality as well. So what is the obvious choice? And mind it, the functions will be from set capital X to capital X. You need to choose such a function which will give a homomorphism and as well as equality. So what will be the obvious choice?
Identity mapping.
Yes, right, correct. Very good. So okay, so you have picked you choose the function identity map. Now if we assume that suppose tau is finer than quarter than tau dash, and now you choose the identity map format. Yeah. Now this identity map is always continuous. Okay. I mean this situation is continuous because tau is subset of tau dash. Now if you can show that this identity map is a homeomorphism, then we are done, right? Correct. If you can show that this identity map from x tau to x tau dash is a homeomorphism, then we are done. Am I right?
Yes, sir.
Yeah. So how you can show that this is a homeomorphism?
Sir, if you will take identity map, then bijectivity is okay.
Yes.
But all we need to do is to check its bicontinuousness.
Yes. Right. But yeah, yes. But use the hint because in this case, bicontinuous is showing, but showing the bicontinuous directly is difficult. Okay. So here use the hint.
Okay, sir.
So you understand how to use the hint? I mean, sorry. Take your time.
So, identity map is continuous.
Yes.
No, identity map may or may not be continuous in all cases.
Okay, but in this case, why it is continuous? Anybody please?
Because tau is contained in tau is like coarser than tau.
Yes, right. Correct.
So if we take inverse image of any open set there, that will lie. It's already there. So identity map is continuous. Now, if we take image of that X, so that image is compact sub. It's a compact subset.
Yes, yes.
So
You are almost there.
in a Hausdorff space,
Yes. Uh, so okay. So continuity is okay. Continuity is fine, right? Now only problem is to the homomorphism. Correct. Hmm? Now the thing is, in the hint, it is given that continuous bijective, and if domain is compact, codomain Hausdorff, there is a homomorphism, right? But then look at the question. In the question is given that tau and tau prime with respect to both topologies, the space capital X is compact as well as Hausdorff. So now consider the identity map whose domain is compact and codomain is Hausdorff. So that's why identity map becomes a homeomorphism. Understand? You understand?
Tau is coarser than tau prime. Is it given or yeah?
It is not given. The thing is, we need to check either they are equal or they are not compatible, right? So we are assuming that they are compatible. Then we are showing that they are equal. Okay. That's not the point.
Yes, yes.
Yeah.
Can you explain it one more time? Like
Hmm.
how identity map is like both side these maps are continuous.
Yes, yes. Firstly, here we are using the hint that if a map F from, I mean, here we are directly using this hint. Okay. That is, if a given function is continuous bijective and is domain compact, codomain housetrap, then F is a homomorphism. Okay, we are going to use this hint. Okay. Now, in order to solve this problem, suppose we have assumed, suppose assume that they are comparable. So, without loss of generality, assume that tau is coarser than tau prime. Okay. Now, consider the identity map x tau to x tau prime. Firstly, this is continuous, right? Is it continuous still? The continuity is clear, right? Okay. So,
Yes, yes.
yes. And now you need to check homeomorphism. Okay. Now we are not checking the homeomorphism directly. Okay. Because we have already given some information that tau and tau prime, both topologies, with respect to both topologies,
Actually, it's not continuous, but it's an open map. Because if you take image of any open set, image of any element like open set, which is the element of tau, that image that open set already there in tau prime because tau is contained in tau prime. So that I is open map.
yes, you are right. Yes, correct. Sorry. So you need to check I to be x tau dash to x tau. Then it will be continuous, right?
Yeah, if tau is smaller, then this map is open map. If tau prime is smaller, then it's continuous. No, that I don't know. But
If
if tau is smaller, then this map is open map.
yeah, I inverse you. Yeah, it's open. Yes, so tau is smaller and tau is on the right side now. Okay, so then it is continuous, right? I mean,
Yes, sir.
yeah. So now you need to check the homeomorphism because it is homeomorphism because in this left portion is a domain is compact and right portion is Hausdorff. Okay, so due to this hint, this identity map is a homeomorphism. So that's why tau and tau dash are equal. Understand? Understand?
Sir, will you please repeat?
Yes, yes. From which portion?
Sir, lastly, what you said.
Yes, yes, yes. So basically, we have proved that identity map x tau dash to x tau. It is continuous. It is we have done, and it is obviously bijective. Okay. Now look at the question. It is given that tau and tau dash are both compact and Hausdorff. Okay. And look at the hint. The hint says that if a map is continuous bijective given, and also if the domain compact codomain Hausdorff, then that map will be homeomorphism. Now, this in this situation, this identity map, this domain is compact because it is given, and the codomain is a Hausdorff because it is also given. That's why I becomes an homeomorphism. Uh, is it fine?
Yes, sir. Clear, sir.
Yes. So it's a homeomorphism. That's why, and it is the identity map. That's why tau equal to tau dash. Okay. So that's the solution of this problem. So, going to the next problem is that so do you know about cofinite co-countable topologies?
Yes, sir.
Okay. So the question is follows. So given X is an infinite set with cofinite topology, you need to check X will be compact. Okay. Any infinite set with cofinite topology will be a compact space. Check. Take your pen. By the way, kindly give your attendance by submitting the Google form.
Sir, this we can do by if we will take any
Yes, yes.
if we will take any open set in cofinite topology, then it will cover X except some finite point because its complement is always finite.
Wait, can you please repeat?
Yes, sir. Sir, if we will take an open cover of X, say AIs are collection collection of open cover of X.
Yes. Okay.
Then sir, each open set which
Yes.
are in the cover of AI
Uh,
has the property that its complement is finite.
correct.
So we can always from this open cover we can always collect a set UI, and for the leftover portion that finite elements we can take some open set containing each element, and that will cover the whole set, and hence X will be compact.
Yeah. Very good. Very good. Yeah. Correctly. Correct. Very nice. So what about others? Does others
Yes, great. Yes.
write a solution or next I should discuss the next problem? So there are how many to discuss? Okay. So okay. So now the next question will be some kind of obvious. In this question, we have seen that cofinite topology will be compact. Okay. Now the next question will be regarding co-countable topology. But in co-countable topology, this is not the case. That is infinite set. I mean, uncountable set in co-countable topology may not be compact. Okay. So for that, consider this. So X is an uncountable set with co-countable topology. Then show that X can't be compact. It's a tricky problem. So try first to construct some kind of open cover, and then you need to check that it will be compact or not. Take your time. It's a tricky problem. Okay. got any open cover? Anybody found an open cover?
Yes, sir. Trying, sir.
Yeah. Okay, so I think it's better to give a hint also.
So
Since
if I take my the UI is it like U1 contains one, like I'm just removing all except all the natural numbers.
one,
I'm taking X is a real number,
hold on,
and
hold on. One second. What is one?
okay,
I mean, X is an
X is X no, okay, for time being, like take X is R.
Yes. Okay.
So my U1 is complement of natural numbers union that one including one, and it includes one. Now U2 like now this is a open cover for R, right?
Is only you have removed only one, right?
I removed all of natural number, but included the except one. One is
Yes.
there.
Yes. Yes. Then what is U2?
U2 is R minus n union U. I'm like union U2 on union 2,
Okay.
taking
And
2 in.
yes. Okay.
So this will cover all of R,
Yes.
and it cannot be finite, like because some n will be left out, right?
Yes. Yes. Very good. Very good. Correct. Correct.
But in general X I don't know. Like
I mean, you have done it clearly. I mean, now try to generalize. It is. I mean, just observe what is N. N is N means you have taken a countable subset, right? So what you will do? So in arbitrary X, take and choose a subset A which is countable. Since it's countable set, you will get an enumeration A1, A2, dot dot dot. So now you will take U1 to be X minus A union A1. Similarly, UN is equal to X minus A union AN. Understand? This, this is the thing. Understand?
yes, yes.
Yeah. Does everyone understand the solution? Let me know. Okay.
Yes, sir.
Okay. So
Sir, I have taken in another way. I have taken mm, A as an open set in this topology, and then its complement is a countable set like a sequence A1, A2, AN, and so on. Then I have chosen BIs in such a way where BIs are all open set such that BI contain A AJ for J is equals to 1.
I don't get you.
Sorry,
How?
for J is equals to I.
Okay, one second. How you choose BI?
So BIs are open set, and such BI contains AI but not AJ when I is not equal to J.
Yes, yes, that is the same thing. The same proof.
Yeah, because this BI, I mean, this UI will satisfy this property, right?
Oh yes, sir. Actually, they are same.
Yes, essentially both are same. No, okay, no. So just I want to know, you know the fact that finite union of compact set is compact, right?
Yes, sir.
So it's a counter-example problem. Find a metric space in which uh, not sorry. So the question is that find a metric space in which not every closed bounded subspace is compact. I mean, you need to basically find an example of metric space where, and you need to find a subspace which is closed bounded but not compact. Okay. So you need to find an example of metric space, and there you need to find a subspace which is closed bounded but not compact. Okay, think about the problem. I will be back after 2 minutes.
So, sir, this in the previous example we proved that in co-countable topology. Hello, hello.
Sir is not there. He told us to wait for 2 minutes.
Okay. So in co-countable topology, if we see that complement of instead of taking natural, if I'm excluding natural numbers, if we are exclude only 1 1/2 1/3 like this set, the same we can construct the same set, right? Now this set is countable. Okay. So it's a complement of countable set. The countable sets are closed, so it's closed and bounded because bounded above by 1, but it's not compact, right? Oh, I'm sorry, X is
Yeah, anyone found the answer? Anybody got the answer? Hello, I'm audible. Am I audible? Yeah. Yeah, right, correct. Experimentally gone up. Very good. So, the come to the next one. Okay.
So, sir, in the
Yes.
previous example,
Yes.
if we take R with co-countable topology,
Because yes, R. I mean, it's a metric space, right? I mean,
oh, okay.
yeah, topology is obvious. Correct. So this problem is tells that suppose we have a compact Hausdorff space X and A and B are two. Sorry, we have a Hausdorff space X and A and B are two disjoint compact subspaces. Then we can find two open sets containing that two disjoint subspaces such that their intersection is also not empty. Okay. So hint will be you can take the hint that uh, use the openness of you can use the openness of x minus say okay this hint you can use or you can use this whatever you want to do. The thing is you need to somehow use to the compactness. For that you need to come up with some open cover. Okay, now the open cover comes from open set, that's why you can choose the openness of x minus say okay and construct some open cover. So try this problem.
Sir, I have a question. Sir, I just can't recall that. Was there any theorem that that a, a compact if we are having a compact subspace of a T2 space, then that subspace will be closed.
Yes, right, correct, it's a theorem.
Hello, sir.
Yes, yes. Sister?
Sir, can I speak in Hindi?
हाँ हाँ, yes.
सर, अगर हम दो मतलब कि ये दोनों सेट है, वो डिस्ट्रीट है हमारे पास और दोनों कॉम्पैक्ट है, ठीक है। तो अगर हम उन दोनों का फाइनाइट जो ओपन कवर है वो ले ले,
हाँ
ठीक है। तो देखो, पहले मैंने यू आई लिया ए का और बी का वी आई लिया, ठीक है। तो अगर मैं यू आई में से मतलब कि ऐसे दो ले रही हूँ, ए में से एक ऐसा पॉइंट ले रही हूँ कि एक्स आई ले रही हूँ ऐसा पॉइंट कि जिसकी मदद से हम यू आई बना रहे हैं, और वाई बी में से हम एक ऐसा वाई पॉइंट लेंगे तो दोनों मतलब कि हाउस डोफ है तो हमें डिफरेंट ही मिलेंगे, मतलब कि इनका जो इंटरसेक्शन है यू आई और वी आई, इनका वो एम्प्टी ही होगा।
ओके, और यार एड टू द आर्गुमेंट पॉइंट।
तो उसी तरह से हम अगर ऐसे ले लें कि सारे के सारे पॉइंट का बी जो भी वी आई है ओपन कवर बी का फाइनाइट ओपन कवर, तो अगर हम उस तरह से एक्स के अकॉर्डिंग वहां से बी के सारे ऐसे ले ले और उसी तरह बी के अकॉर्डिंग अगर हम यू आई से ले ले तो दोनों मतलब कि नॉन मतलब कि इनका इंटरसेक्शन होगा वो एम्प्टी ही होगा।
Yes, sir. So what you're doing in visible is that first you are considering only A, and then for each point of B you are taking an open cover inside A, and then using compactness you are getting a finite subcover which contains capital A, and on the other hand you will get some open cover, so open set containing that point. Now in the B you are doing the same thing, right? And this is what you are giving the argument, right?
Yes, sir.
Yeah, good, very good. Yeah, you are always correct. What about others? Okay, for others I am giving some hint also. Okay. Hint will be as follows. So the hint will be as follows. Suppose if we choose any point outside that capital A, then also we can find some open set W containing X and some open set Z. Sorry, I mean Z is also open. Okay. So open set Z containing A, so the W intersection Z is also empty. Okay. So first this is the end, and using this hint we can prove this problem. Okay. So now try to figure out the solution. go and take your time, try to figure out the solution. Or first you assume the second hint, and then assuming that hint, try to solve this problem. Later we will see that how to prove that hint also. Okay. First you can assume this hint, and then using this, try to solve this problem. Anybody figure out the solution? Anyone?
सर
Yeah.
सर हम जो फर्स्ट सीन थे उससे हम ऐसा कह सकते हैं कि जो ए का जो फाइनाइट ओपन कवर होगा और जो मतलब कि बी है उसका जो फाइनाइट कवर होगा ओपन कवर
Yes.
वो दोनों है वो एक दूसरे के साथ मतलब कि इंटरसेक्शन करेंगे तो एम्प्टी मिलेगा। तो अगर हम यू है वो ए का फाइनाइट ओपन कवर ले ले और बी है वो बी सॉरी वी है वो बी का फाइनाइट ओपन कवर ले ले तो ये हो सकता है ना?
Yes, you are in the right track. You need to figure out some things, but you are on the right track. Very good. So just whatever you said, just write it down, and then you can easily figure it out. Okay? Whatever others, who else has figured out this problem? Who else? Who else has figured out this problem? Just let me know. Or you can raise your hand or write it in the chat also. Okay, so let's do this. Let's do the solution. Okay, so firstly we will assume the hint, then using that hint we will solve this problem, and then after solving that we will prove the hint also. Okay, so for each, so take a B belongs to B. So B does not belong to here, right? So by the hint, here exists an open set WB containing A, is an open set, and ZB containing B. ZB is also open, such that WB intersection ZB is empty. Okay. Now for each B we get such open set, right? So this ZB, B belongs to B. This is an open cover of B, right? So it will have a finite subcover because B is compact. So let B is equal to union ZBI, I is equal to 1 to n. So now for each B belongs to be WB contains capital F. Okay. So if we take the intersection of this final WBIs for I equal to 1 to n, this is an also open set containing A. Okay. And the each ZBI is equal to B. Okay. Now our claim is that if you take U equal to this and P equal to this, now claim is that U intersection is open. Sorry, empty. Can anybody tell why this is true that U intersection B is empty? Anybody? I mean, this directly comes from the construction, but anybody please tell. Remember that how we choose these things. WB is an open set containing A and ZB is an open set containing each small b, so that the intersection is empty. Now, using that fact, can anybody please tell that why intersection B is empty? Anybody please?
So,
Yes.
so if we suppose that it is non-empty, if some element belongs to their intersection,
Yes.
U and V. So
Yes.
T belongs to be the intersection of the WPI. So it belongs to each WPI. And also T belongs to the ZPI for
Yes.
some BI.
Yes. Correct. Very good. Yes. Then.
So both intersection is non-empty, which contradict the hypothesis.
Yes. Right. Very good.
Yeah.
Yeah. So that's why this intersection is empty, and that's why the problem is solved because here we only need to find U and V with intersection, right? So that's our candidate for you. That's the candidate U and that's the candidate V. Okay. So this is a solution. Does everybody understand the solution? Or should I repeat this just Does everybody understand the solution? Anybody has any doubts or any confusions? Please let me know. I hope that everyone understands the solution. So, so using that hint, we have solved this problem. Now, we are going to prove the hint. Okay. So x does not belong to the first. So this is our hint, and this is the point. Okay. So, so choose A belongs to A. Okay. So obviously A is not equal to x, right? Now the space x is given to be house dot. So there is an open set UA containing A and open set BA containing X, both open. Such that UA intersection B is empty. Okay. So this is what for each point of A, we are getting open set UA, and correspondingly we get open set BA containing X. Okay. So now A is given to be compact, and this UA forms an open cover of A. Sorry, this is an open cover. So it must have finite subcomponent. So A will be equal to union of UA I is equal to 1. Okay. So this implies what? So finite number of points AI which covers the whole A, right? And so if we take the our U to be union UAI and V to be intersection VAI, then V is an open set, is an open set containing A, and this U contains capital A, and exactly the same reason as previous, U intersection is empty. So this proves the first hint. So do you understand this proof of the hint? Does everyone understand the association?
Yes, sir, clear.
Yeah, okay. So, consider select components. Okay, so just I want to know one thing. So, in this problem, uh, this is the hint we have used, right? So, do you know the proof of this hint? Just do you know the proof of this hint? Do you know the proof of this hint? Or okay, so I mean, don't be silent. Please let me know. Do you know the proof or not?
No, sir.
Okay. So let's prove it. So the left A x2y is a continuous and bijective, and given if x compact, y house dot, then show A to close. So the question is follows. Suppose f is a function continuous bijective from x to y. Given the domain is compact and codomain is Hausdorff, then we need to show that it is a closed map. And if we can show that it is a closed map, then obviously this says that it is a homomorphic. So try to show that F is a closed map. Okay, it's a straightforward problem. Try to show this. Yes, very good, Pila. You have said correctly, very nice. Yeah. Yeah. So that's the solution. What she wrote in chat also. So let's move to the next move. Now next one. So consider the first coordinate projection. First question is it compact? Is it closed? And the third question is why compact? Why not closed? So first try to realize that whether the first coordinate projection map is a closed map or not. Okay. First solve the first one. I mean, obviously, from the second question, it's clear that the phi one may not be closed map in general. So try to construct in some x and y for which the phi one is not a closed map. Okay. So try to construct a counter example. Think about it. Also, please share your attendance to the submitting the Google. Anybody found in a counter example?
So if we take x will be a positive real number and y is equal to real number. And the map defined as if x
And y will be what?
a real number.
Real number. Okay.
And the map defined as xy map to be the product xy.
X comma y equals to a product. So you're taking a product map. No, the map is already given, right? Pi one, right? First coordinate projection. This is the map you need to take. Okay. I mean, you can't change the map, right? Understand?
Yes, sir.
Yeah. So try to construct some counter example.
Sir,
Yeah.
then the same map will work if we take 1 by n in R. So it is closed
Sorry. Can you please repeat?
1 by 1 by 1 by n 0.
It's 1 by n, comma 1 by n, comma. I mean, it will be a Cartesian product, right? So 1 by n, comma what?
No, sir, I'm taking in a real number, only the real number, y space, the closed set.
Okay, y. No. Okay. So what is your x?
So the positive real number.
Okay, and y is equal to real
All
number.
of real.
Okay, and okay. So okay. So what is the step now you are taking?
So 1 by n union 0. Uh,
Its image is 1 by n, right? I mean, no. The thing is, 1 by n comma 0. This set is not itself closed because 0 does not belong to this domain, right? So I mean, the domain subset is not a closed set event. So you need to take a closed set whose image is not a closed. Okay. So consider the following example. Take C to be.
Hello, sir.
Yes, listen.
So if we take x is equal to low r real line r and with a lower limit topology, and if y is equal to r and with a usual topology, then it will be work.
So okay, so 1 by 1 0. No, then also it will not work because this state is not closed in that product topology. Okay, it is not closed there. So
So
this
if we take a closed set in a lower limit topology, then it
yes.
may not be in usual.
No, that I mean, so you are taking, suppose you are choosing F, which is closed in the lower limit, right? And then you are taking the set F crosser, correct? I mean, it's pi one will be F again, but since F is closed in the lower limit topology, so F will be closed in user topology also. Because if I mean, so you know the fact that lower limit topology is finer than usual topology, right? So since tau u sub is
Yes, sir.
tau u subset of tau l, so tau l complement is a subset of tau u complement. Okay. Now, if a set is closed in tau l, that is f belongs to tau l complement, then it will also belongs to tau u complement. So closeness in the bigger topology remains closed in the smaller topology. Okay. So this example will not work. Understand?
Yes, sir. Yes, sir.
Yeah. So consider the following counter example. Take P to be all those xy belongs to R2 such that xy is equal to 1. Okay. So this is a closed set in R2, right? And its graph will be like this. Now what will be the pi 1c? Pi 1c will be R minus 0, right? So pi 1 will be R minus 0, right?
Yes, sir.
Yeah. So which is not closed. So pi 1 not closed map in general. So that's the first problem. Now for the second problem, is that if the y, that is the second coordinate space, capital Y is compact, then pi 1 will be a closed map. First try to prove it using the tube lemma. Okay. So by the way, there are many versions of tube lemma. So can anybody please state that tube lemma? Don't hesitate. Whatever you know about tube lemma, please tell. Don't hesitate. Anybody please state the tube lemma? Okay. So let me state the tube lemma first. Let y be compact and x be an space, and let x not be a space. Let n be any neighborhood of x naught crossing y. Then there is a neighborhood W with containing x naught such that this neighborhood contains W cross y. That is, if we consider this slice x naught cross y, and if we have some neighborhood in here, then we'll get a neighborhood W around x such that W cross y is fully contained inside capital N. Okay, so this is a tube lemma. I mean, this is the one version of tube lemma. Now, using this version of tube lemma, try to show that if the y is compact, then the first order projection will be closed map. think about it?
Sir, will you please show the second question?
Yes, yes. So this is the second question, that is, if y is compact, then check show that phi 1 will be the closed buffer. And the hint is you need to use the tube lemma, which that version of tube lemma which we have just seen. Okay? Use that version of tube lemma. Anybody have any idea or got some way to solve this, or any possible guess how to approach this problem? Okay, so okay, so let's see how to do it. Okay? So we need to check that pi is closed, right? So what we will take? We will take a closed set from x cross y. So let x be a closed set from x cross y, and we need to show pi 1 is a closed in x. Okay. So what we will do? It is equivalent to showing that x minus pi 1 is open in x, right? So take an x outside pi 1 of x. Okay. This implies what? X cross y does not lie in capital F for all y belongs to y, right? This implies what? X cross capital Y is a subset of x cross y minus x, correct? Now, since F is closed, this is an open set, right? Now, here we need to use the tube lemma. So there is an open set Wx containing x such that Wx cross y is contained inside x cross y minus x. And this implies what? This implies Wx is contained inside x minus pi 1 x. So yeah, so So this tells that x minus closed. So yeah, this is the solution. So you want everybody understand? Does everyone understand the solution? Is there any doubt or confusion in the solution? Please let me know. Or do I need to repeat the solution? Please tell me.
Sir, please repeat once.
Yeah. Okay. So so what we need to check? We need to check that pi1 is a closed map. Okay. So what we have done? We have taken a closed set in x cross y, and finally we will show that pi1 of f will be closed in x. Okay. And which is equivalent showing that complement of pi1f is open in x. Right. So in order to check the openness, what we will do? We will take we will take a point outside pi1f. I mean, this is same as saying that that point we have taken is from x minus pi1. Okay. So this implies what? X comma y does not belongs to f for all y belongs to y. So is this line clear?
Yes, sir.
Okay. So this implies what? X cross capital Y subset of, I mean, x cross capital Y is disjoint in capital F. That is same as saying x cross capital Y is a subset of x cross Y minus capital F. Right? Understand?
Yes, sir. And then we use tube lemma.
Yes, right. Right. Then we use the tube lemma, so we get some open set Ws containing x. So the Wx cross Y is outside capital F, and this tells that Wx is subset of x minus pi 1f. So this tells that x minus pi 1f is open, and this tells that pi 1f closed. Right. You understand the solution? Do you understand?
Yes, sir.
No. Do the next problem. Let f x to y be a continuous map and y compact plus house law. Show that f sorry show that f continuous if and only if the graph f, that is this closed. So the question is that suppose f is a map from x to y, and given also that y is compact and house structure. Okay, now we need to check that f will be continuous if and only if graph f, which is the collection of all possible tuples of the form x comma fx, that graph f will be closed in x cross y. Okay, so this is what you need to show. First think about it, how to do this. Okay, so I need to give a hint also because we don't know. So first, so hint is that a space x is house dot. I mean a space z is house dot. If and only if it's diagonal, that is this thing. So use this hint to show that if continuous implies graph is closed. Okay. Use this hint to show that f continuous implies graph of f is closed to x plus y. Anybody for the way? Anyone? Okay. So for the first part, it will be as follows. Okay? So we will use the hint. Okay. So consider this function f. I mean assume first f continuous. Okay. Now define a function f from x cross y to y cross y. Okay. Use the function f of x equals to x comma sorry yeah fx comma y. Now this will also be continuous. F will be also continuous. Capital F will be continuous since f is continuous. Now y house dot. Okay. So f inverse the diagonal of y means what? This will contain all those x comma y such that fx equal to y. I mean, so basically this is all those x comma fx such that x belongs to x. So this is what? This is graph of f, right? Y house drop, capital F continuous, diagonal Y closed, so F inverse diagonal Y closed, and this is graph F, so this is closed in x cross Y. One second, what happened? Sorry, due to some issue suddenly. Just hold on, sorry. Can you see the screen?
Yes, sir.
Okay. So yeah, now since Y is house drop, so oh sorry, it got deleted automatically. Yeah, okay, so let me write it again. Since Y is given to house drop, so F inverse of graph Z, it will be closed in x cross Y, right? Now, what will be F inverse of del Z? It will be contain all those point x comma y such that y is equal to fx. It is by definition, and this is what all possible point x fx such that x belongs to x, and this is nothing but graph of f, right? So we get what? That graph of f is closed in x cross y. So if we choose our f, small f, to be continuous, this tells that graph of f is closed in x cross y. So do you understand this direction?
Yes, sir.
No. Okay. Now, okay. So do you first try the converse direction, or I will write down the solution? What do you want? Please let me know. Do you want to try the say first direction? Okay. So let's go the converse direction. So let graph of f be closed in S first. Okay. We need to show f is continuous. So now consider it graphically. Okay. Suppose this is our f. Okay. So in order to check f continuous, what we will take? We take f subset of y be closed. So choose a closed set. Okay. F. And then consider this portion. So consider this portion. Then so consider this portion. This portion is what? This portion is pi 2 inverse f. Okay. Now if we project, I mean, yeah, this is pi 2 inverse x intersection graph of it, right? Now if you project this portion here, so this portion will be of pi 1 of that thing, and the thing is, observe that pi 1 of pi 2 inverse f intersection graph of f is equal to f inverse f. I mean, this obvious. If this is f, then this portion is actually f inverse f, right? So we have this thing equation, and it is given that graph f is closed. Since graph f is closed, so and f is closed, we have taken f is to be closed set, and pi 2 is always a continuous function. So pi 2 inverse f intersection graph f is closed, and since y is compact, so pi 1 of this is closed, so f inverse is closed. Okay. So do you understand the argument, or you want some confusion? I mean, okay, let me write it down. Graph f closed. Okay. F closed in Y. So this implies pi to inverse F closed. And so this implies pi to inverse F intersection graph of F closed. This implies pi 1 of pi to inverse F intersection graph of F closed, because Y is given to be compact. And so this tells that F inverse F closed in X. Do you understand this solution?
Yes, sir.
Okay. What about others? Does everybody understand this solution?
Yes, sir.
Okay. Okay. Now, okay. So consider this
I
problem.
have a doubt.
Yes. Yes. Please tell. Please tell your doubt.
Sir, that is from the lecture notes. Sir, actually, sir, differentiation on the Banach space, sir, I am unable to understand the geometry of the differentiation on the Banach space. Like, if you will be clearing these in the next some
Yes.
lectures,
Yes.
then that's okay.
Yes. Yes. In next session, you want to do the differentiation of the Banach space, right? Okay. Sure. Sure. In the next live session, I will. I mean, in the next week, I will definitely do it. Okay.
Then that's okay, sir.
Yes. So, okay. So consider. Yeah. Okay. Show that. So do you do? Everybody knows that R with K topology. Does everyone know R with K topology?
Yes, sir.
Okay. So now consider, show that closed 0, 1 is not compact in R with K topology. I mean, so basically to consider open, right? I mean, sorry, open cover. Okay. So try to consider open cover. Try to construct some open cover. Take your time.
Sir, if we will take a open cover of 0, 1 by the interval -1 by n, 2, will that work?
-1 by n. Why you are going to study the -1 by n? I mean, firstly, -1 by n, 2, it contains an open set of the form -1, 2, right? It obviously contains closed 0, 1, obviously, right? So you need to construct some open covers which can't have finite subcover, right?
Sorry, sir, what you said. I just got disconnected.
So construct an open cover like -1 by n, 2, right? But I mean, if we take n equal to 1, then this open cover contains an open set of the form -1, 2. Now, sorry, this -1, 2 all, sorry, I don't know where they should be notified actually, sorry. Hold on. Can you see the screen?
Yes, sir.
Yeah. So, if you, yeah, if you, I mean, if consider open set -1, 2, it already contains closed 0, 1, right? So this is itself the finite subcover. So choose some open covers which don't have finite subcover. Understand?
Yes, sir. I
Yes.
found. Sir, like if you will take sets like these and remove the points of the form 1 by k, where k are natural number, because these will not be exactly open in RK.
No, no. Open set of RK are, I mean, bases are what? Bases are open set of this form AB and also open set of this form AB minus K. These are also bases. These are also open. So any open interval is already open in RK. I mean, is also open in RK. Okay. So there is no harm in it. You understand the point? Do you understand the point?
Yes, sir, got it.
So okay. So anyone found some open covers? Okay. So choose the open cover as follows. Take un to be 1 by n, comma 2, and the open cover will be un union the set -1, 1 minus k. So this whole I mean this sorry I mean this thing sorry this whole collection even along with -1, 1 minus k forms an open cover. Okay. Now it is easy to observe that this can't have finite subcover, right? This can't have finite subcover, right?
Yes, sir. Clear.
So, okay, so do you know about limit point compactness?
Yes, sir.
Okay. So, okay. So, uh, show that closed 01 is not limit point compact as a subspace of RL. Closed 01 is not limit point compact as a subspace of RL. So what you need to do, you need to find an infinite subset uh, that has no limit point inside R L, right? So try to construct some finite set. Okay, so for anybody for the any infinite set inside closed 01.
Sir, like if we will take the infinite subset 1 by n
1 by n.
of 0, 1.
Yeah, right. So you're choosing set 1 by n, right? So firstly, if you take the set 1 by n, then 0 is a limit point because if we take any neighborhood around 0 in lower limit topology, it will look like closed A open B, right? So that's why you need to take the set infinite 1 minus 1 by n, its limit point is 1, right?
Oh,
Now, if
yes,
we,
sir.
yes, right. So this will not hold because one is in the lower limit topology the close bracket in the left side, so that's why this one cannot be limit point of the set 1 minus 1 minus. Okay. So that's why it's not limit compact. Okay, so do you know about locally compactness?
Sir, I read it, but I forgot
Okay,
at
okay, no.
this moment.
Yes, no. Okay, anyway, so on the next class we will start with locally compactness, and as we have told that differentiation on the Banach spaces. Okay, next day we will discuss also. So yeah, for today, let's stop here. And if anyone has a doubt, so please ask in the next session. Okay. Okay. So right now I am ending the session here.
Thank you, sir.
Thank you, sir.